Good afternoon to everyone. I think that we are all here, so if you're okay with this, we can start. I'm Valentina Costa from the University of Genoa, and today I will be the chair of this session. So first of all, I will just double check that you are here. So the first to present will be Chiara Garau, Mana Dassum, and Reza Askarizad, and I think the presenter is online. Is it right?
Yes, of course. Hi, everyone.
Hi, and the second contribution will be by Giulia Pedilarco, Barbara Caselli, and Michele Zazzi. Is here. The third one by Veronica Calaiera. And then Martina Carta, Roberto Ventura, Stefano Raccagni, Michele Pezzagno, Davide Vetturi, and Benedetto Barabino. In representation of all the teams. And then Carmen Guida, Paolo Battista, and Gerardo Carpentier.
Carmen, in a few minutes will join us.
Okay. So I don't know if you want to wait, maybe.
No.
We can start. Okay. So I think that I'll let the floor to the first presenter. So Reza, please go ahead. The floor is yours.
Yes, of course. Thank you very much. First, let me share my screen. Can you see my screen?
Yes, it's all good.
Okay, thank you very much. Hello, everyone. Thanks for the opportunity to present our research. I'm pleased to present our study titled Integrated Computational Design and Space Syntax in Urban Planning and Design Education, a data-driven pedagogical model, on behalf of our team at the University of Cagliari in Italy, Professor Chiara Garau, Dr. Mana Dassum, and me. My name is Reza Askarizad. I hold a PhD in urban regeneration and sustainability at the Polytechnic University of Madrid in Spain. I had a couple of years of experience as a postdoctoral research fellow at the University of Cagliari and served as an official scientific editor at Elsevier. Today, we are going to share our experience on how we have intermingled a well-established computational and spatial analysis tool into the pedagogical model. Here is the roadmap of this presentation. I will first explain the research motivation and gap, then introduce the methodological framework applied in an urban design studio in Cagliari. After presenting the computational and empirical analysis, I will show how these were translated into design interventions and finally discuss the pedagogical implications and contributions. Let's start with the question that why computational design in urban planning education is important. Computational design uses algorithms, data-driven modeling, and simulation techniques to support spatial design decisions. In urban design, it extends beyond digital representation by enabling the analysis of streets, networks, visibility, accessibility, and movement patterns by quantitative methods. These tools allow urban spaces to be understood not only as physical forms, but also as dynamic systems whose performance and function can be measured and evaluated. As a result, computational design provides an evidence-based approach to urban design that can support decision-making in the design process and optimize the final project. The existing literature on these issues mainly focus on parametric design, simulation, gamification, and digital modeling. However, the key gap addressed in this study is that space syntax is usually treated as an analytical tool rather than as a pedagogical structure. To address this gap, the main aim of this study is to introduce a systemized data-driven pedagogical framework that incorporates computational design into learning process of urban design studio. In this context, space syntax is a theory and methodological approach in a spatial analysis that identifies accessibility of urban network systems and potential movement and social encounter patterns of users in urban spaces, which is operationalized through different computational software packages such as AutoCAD GIS and most importantly, DepthMap. The suggested model is introduced and discussed by means of an international urban planning studio organized at the University of Cagliari in an Erasmus program setting. In particular, the research aims to reveal how configuration-based tools can be used as an organizational guide through the sequential phases of spatial diagnosis, analytical assessment, and design intervention in a studio setting. The study aims are threefold. First, to codify an executable workflow for the integration of computational processes into the studio process. Second, to show how the implementation of this framework can contribute to analytical coherence and evidence-based decision-making in student projects. And lastly, to investigate how embedded computational processes can be used to improve the quality of evidence-based decision-making in students' projects. Giardini Pubblici, located in a historic center of Cagliari, was selected as a case study for applying the proposed computational pedagogical model. It is a representative example of a group of students' work developed during the International Urban Planning Studio. The methodology follows 5 sequential steps. First, students perform a spatial diagnosis using computational and observational methods. Then findings are translated into design interventions, which are then evaluated through post-intervention analysis. Afterward, the workflow is formalized into a pedagogical model and finally assessed through comparison with traditional studios and SWOT analysis to better understand its pros and cons. The analytical framework consists of 2 complementary steps. The first is computational analysis, which uses axial analysis and VGA and agent-based simulation to evaluate the spatial configuration and movement potential of the study area. The second is empirical observations through gate counts, which records actual pedestrian movement patterns. And by combining computational prediction with field observation, the framework provides a more robust and evidence-based evaluation of urban spaces. At the macro scale, axial analysis was used to evaluate the street networks surrounding the study area. The results showed that the main streets surrounding the park have the highest integration values, indicating that the park is located along the strategically accessible urban routes. This suggests that the surrounding area has an accessible and organized spatial structure. At the micro scale, VGA was used to determine the visual properties of the park. The visual integration map evaluates how visually accessible each location is within the entire park. For instance, highly integrated areas are concentrated along the central axis at major intersections, suggesting that these spaces are more likely to attract movement and social activities. This will be complemented by dynamic agent-based analysis and simulation by releasing virtual agents to predict how people can potentially move through or perhaps encounter within the designed space. To validate the computational analysis, empirical observations were conducted using gate count method. This technique records the number of pedestrians entering and exiting the park through selected access points during specific observation periods at different time intervals of weekday and weekends. The comparison between empirical observation with computational analysis will allow to validate the methodological approaches with one another. After completing the analysis, the results were systematically translated into design strategies rather than treating the analysis as separate evaluation tests. Students were encouraged to integrate the analysis of results to optimize their design and planning. This established a clear link between spatial diagnosis and the proposed design interventions, ensuring that every design decision was supported by analytical evidence. After implementing the proposed design interventions, recalculated analysis showed improved efficiency in movement patterns. The statistical correlation shows that the proposed design improved the spatial legibility after design intervention. The increase in R-square indicates a more coherent and intelligible spatial structure. This slide represents the core contribution of the paper. The model formalizes computational analysis as an educational framework rather than merely a technical tool. In this model, students continuously move through diagnosis, intervention, validation, and feedback, creating a closed-loop learning process. The comparison with traditional studio highlights a shift from intuition-based design toward evidence-based reasoning. In this pedagogical model, urban design moves beyond personal taste to follow an analytically valid evidence-based research process. To evaluate the proposed pedagogical model, a SWOT analysis was conducted. The strength of this pedagogical model includes a structured evidence-based workflow that improves analytical transparency and support informed design decisions. The main weaknesses are the technical learning curve and the additional time required to apply computational tools. The opportunities lies in integrating emerging technologies and extending the model to other educational contexts and enhance the research-based education for the design. The main threat includes limited computational reasoning, differences in educational digital skills, and the risk of overemphasizing quantitative analysis over design creativity. The SWOT analysis shows that the model has a strong educational potential, provided that these implementation challenges are carefully addressed. In conclusion, the study shows how space syntax can structure the entire urban design learning process. The proposed model enhances methodological transparency, supports evidence-based decision-making, and introduces a reproducible framework for computational urban design education. Thank you for your attention. If there is any doubt or ambiguity, I will be happy to clarify.
Thank you, Reza, for your contribution. And I don't know if the audience has some questions. No, I will just add a brief comment because I was thinking of what you said of the improvements that this kind of approach can actually introduce in the educational process. But I was wondering whether you had tested also like an ex ante and ex post evaluation of the improvement actually that students have from this methodology, because I was thinking about the strategies that they are proposing. And in some cases in our classes, we ask them to propose some strategies at the beginning, following their intuition, and then to compare them to the data-driven strategies that descend from the application of the tool. And I was wondering whether you have thought of any of these things, or why not?
Yes, of course. Thank you very much for your brilliant comment. Of course, there are different kinds of approaches for the educational learning process, especially in design studio. Our specific approach to apply in which has been applied in our setting was based on the fact of that firstly try for provide the opportunities for the students to analyze the existing condition of the related parts and try to analyze the current condition as it is in the real world, and try to identify its pros and cons, benefits and advantages and disadvantages to understand well their current conditions. After that, what we asked them was based on their specific intervention design. They need to propose some specific design interventions so that after intervention, they can redraw their intended design layout and try to reanalyze based on their new intervention in order to assess if their new design and proposed design has been improved in terms of accessibility, social encounters, or if it is provided a better setting for the pedestrian and users of that specific parts. So based on this strategy, the main assignments of the student has been designed, and that is this workflow of work.
Thank you so much.
You're welcome.
Not further comments? Just thank you, Reza.
You're welcome.
And we will introduce Julia in the second contribution.
Il PowerPoint. Perché non lo vedo?
Good morning, everyone. I'm Giulia Pedilarco from the University of Parma, and today I'm going to present you a work that my professor Barbara Caselli and Michele Zazzi are doing at the Department of Engineering and Architecture. The contribution is titled Associations and Public Facilities as Infrastructure of Slowness, Proximity and Sociality at Neighborhood Level. In this presentation, I will show how social infrastructure can support the implementation of the slow neighborhood model, focusing on the concept of relational proximity through the case study of the San Leonardo neighborhood in Parma. This research originates from an agreement between the University of Parma and the Association Città Slow International. Within this collaboration, our department is working on two research lines. The first one is updating the accreditation criteria for cities, for small cities, so with up to 50,000 inhabitants, while the other one is finding accreditation criteria for neighborhoods in medium and large size cities for the Città Slow Metropolis program. The San Leonardo neighborhood in Parma represents an excellent pilot case for this program. In fact, our research group has been studying this neighborhood for several years, so we already possessed many knowledge about this neighborhood. And for this reason, we decided to catch this opportunity to investigate another information about the relational proximity. Therefore, the main question guiding our research is: can social infrastructure become the foundation of a slow neighborhood? The context is based on the urban context. In fact, cities are increasingly characterized by speed. Speed, in fact, shapes the way we move, the way we live, and how we consume, and even how we interact with each other, with one another. And as a result, the concept of slowness is often misunderstood. In fact, slowness is associated with nostalgia, with rural places, or even resistance to innovation. However, recent initiatives such as Città Slow Metropolis suggest that slowness may also represent an innovative strategy for improving quality of life in urban neighborhoods. Despite the growing interest, today there is not an operational framework for applying slow principles to the neighborhood. And for this reason, we argue that slowness should not be interpreted simply as reducing of speed. Instead, it can become a strategy that enhances quality of life and strength, and can also strengthen the relational proximity through social infrastructure. Our work is grounded in the philosophy of Città Slow International Association, which is a movement founded in 1999 and which promotes the city of good living. Città Slow encourages cities to improve quality of life and preserving local identity, traditions, and but meanwhile they want to embrace the innovation, environmental sustainability. So today the network reached 33 countries with 308 city members. So it's a very large network. And building on this experience, Città Slow Metropolis program explores how these principles can be applied to the neighborhood. Neighborhood of middle and large cities, as I already said. And in this research, we interpret the slow neighborhood through three dimensions of proximity, which are spatial proximity, in which we have active mobility, so walking and cycling, and also we want to reduce car dependency and improve health and safety. Functional proximity, so the access to services, to public spaces and local activities to increase the local economy. And the relational proximity, which is the main framework in which this topic is about. So relational proximity is based on social infrastructure as association, organization, informal groups of the neighborhood, and social cooperatives. And this social infrastructure can enhance social cohesion, sense of belonging, and civic engagement to reach a happier, healthier, and safer neighborhood. So, to investigate relational proximity, we combined expert and situated knowledge of the neighborhood. In fact, we integrated quantitative spatial analysis with qualitative information. The first step, as you can see, consisted of collecting data from Geoportal and from Municipality of Parma and National Register of Third Organization, Sector Organizations. In the meanwhile, we also collected data from semi-structured interviews that we did with the association, public facilities, so many actors of the neighborhood, and collected this data on a GIS database. After that, we reviewed several experiences developed within both the traditional Città Slow network and the recent Città Slow Metropolis program. Although these cases have many differences between them, they have the same pattern about community participation, about strengthening local identity, and for this reason we understood that relational proximity can be an important dimension for the slow neighborhood. The San Leonardo neighborhood is, as I said, in Parma, in the Emilia-Romagna region, and it is a medium-sized city with 200,000 inhabitants, and the San Leonardo neighborhood has more like 20,000 inhabitants. It is also characterized from very high foreign citizens. It's like 25% of the population of this neighborhood. And historically, this neighborhood developed around the railway station. So all the city's industrial activities were there, like Bormioli Glass Factory, maybe you know. And today it is undergoing a very heavy transformation. And for this reason, it's a very dynamic neighborhood of the city of Parma. And the map on the left shows the distribution of public facility and green areas across the neighborhood. As you can see, there are many schools, sports facilities, healthcare services, and churches and urban parks that can provide many activities and social interaction through the neighborhood. While the map on the right, yes, on the right, is about where the headquarters of associations and social cooperatives of the neighborhood are. And an interesting aspect of this organization is that many activities are concentrated in 2 points, which are Casa del Quartiere and Officine On-Off. And these organizations promote many activities in a cultural way, educational programs, environmental, and also social support. To better understand the role of this organization and these actors, we carried out these semi-structured interviews. Our goal was to understand how they offer their activities to the neighborhood and to the people that live in the neighborhood, and how they can contribute in the future to the neighborhood. So the protocol was organized in 7 sections, which are the role of the organization, the citizen participation, if they have collaboration with other organizations or with the institutions, what they think the neighborhood can transform in the future, and urban regeneration, if they had already had processes with transformations or urban regeneration. And we interviewed many organizations with different missions. Some mainly support vulnerable groups, such as Ancescao and Fiorente. Other promotes cultural initiatives or entrepreneurship, like in the neighborhood, there are many committees, local committees, that focus on local urban issues. And but many of them said that the major problem was about insecurity and urban decay. After combining the GIS analysis with the interviews, we assessed the opportunity generated by social infrastructure. In the left map, each colored circle represents different types of opportunities available in the neighborhood. Rather than showing individual organizations, the map illustrates the concentration of activities in each place. In the northwestern part, where is located Casa del Quartiere, there are many activities. In particular, sociality, culture, and assistance are the most present functions. While in the second map shows the age groups targeted by these initiatives. That we differentiate between until 15 years old, from 16 to 30, from 31 to 50, from 51 to 75, and over 67 years. And the results indicates that opportunity exists for all generations, but the majority is for people from 15 to 50 years old. And this suggests that the social infrastructure is very rich, and also the distribution can be more balanced in the neighborhood. And combining the maps with the interviews, three main aspects, we noticed three main aspects. There is a very dense network, but in the meanwhile, an unequal access to the spaces, and that the social infrastructure alone can't be effective, because this effectiveness comes from the accessibility to these spaces and a long-term continuity in frequenting these spaces. The relational proximity should not be understood as a static condition. It is a dynamic process that depends on continuous interactions between local actors, spatial distributions, and institutional support. And moreover, this means that relational proximity cannot simply be planned by constructing new buildings or new facilities, but it is important to frequent these spaces and have relations between each other. And moreover, another interesting thing is that relational proximity is for leisure time, because urban planners can't work in the sphere of working time, but just on the leisure time and how people live this time. Through social infrastructure and relational proximity, we can encourage people to have more relations. And moreover, we notice that a Bermioli site can be a very important center for the neighborhood, as we noticed from the interviews. And to conclude, this research demonstrates that relational proximity can foster this slow neighborhood model, and that it actually can create opportunities for participation, belonging, and social cohesion. And our research also combining spatial and interviews, spatial aspects and interviews, allows us to understand how these functions are lived in everyday life. And yes, so it was very, very interesting, the research that we conducted.
Well, thank you, Julia. I don't know if there are any questions from the audience. So I will go again, just with curiosity. I was thinking about the map that you showed us, and did you focus on specific personas, specific user profiles that may encounter criticalities or difficulties in accessing the social opportunities from the neighborhood?
Yes, we noticed this problem because many associations are founded by retired people, because they have more time respect other people. And for this reason, maybe they provide things that they are interested in. And moreover, as I said, this neighborhood is mostly with foreigners, citizens, and there aren't many activities in which they are involved. Thank you.
I will ask Veronica to come here to present the work on remote work and residential attractiveness across the center periphery gradient.
Good afternoon, everybody. Thank you, Valentina, for introducing me. Thank you, Zara, for your help, and thank you all for being here. Today, I will talk about remote work and residential attractiveness across the central periphery gradient. I will start with a very basic question. What makes a residential environment attractive? And usually this question involves a trade-off. Central localities are usually valued for access to jobs, to communications, to services, to infrastructure, to transport, etc. On the other hand, the suburban locations, symbolized by this highlighted housing, is often valued for space, for autonomy, for privacy, and sometimes also for better environmental conditions. Of course, not always. So, and my hypothesis is that the remote work changes the conditions of this trade work. Remote work did not only change where we work physically, but it also work how we evaluate where we work, where we live. And this is my core argument for this paper. So my question is, what becomes more attractive when we can commute in a reduced way? So for my argument, the commute is central. It's not about only the transportation, but it's not about mobility issue. This is what turns distance into a daily cost. Before the pandemic, commute connected the home, the workplace, and the inner city, and it made the central location very valuable. At the same time, it made peripheral or suburban space more costly because that space usually came with longer distances. And when we experienced first remote work, and later it was very much enhanced by the pandemic lockdown, this balance was disrupted. So the value of access, of course, does not disappear, but the cost of distance became less dominant for those who can work remotely. And this is my argument, and this is why I frame the pandemic also as a coordination shock. This is also why 2020 period is very valuable for me. It's open, let's say, the unique analytical opportunity window. It gave us an opportunity to study the mechanisms that were not revealed earlier. We could ask the respondents how they evaluate and how they re-evaluate their housing condition in this particular moment when they experience all this change stuff. So the survey was conducted in Poland in 2020 in the 2 last months. It was the period of lockdown. Altogether, it was a national data set, representative one for quota sampling, and it was 817 employed responders, and about 1/3 of them were remote capable, and about 2/3 of them were non-remote capable, so they had to travel to their workplaces at least several times per week. We also captured the settlement gradient. We asked responders how they perceive and define the place they will live. And there was the gradation from the large city to suburbs of large cities, medium-sized cities, village, small town, and open rural area. And the 2020 was a specific period. From one side, as I mentioned, it was a very rare analytical opportunity. From the other hand, it was a very unique and short moment. So we do not claim that we study the whole changes in perception or longitudinal changes. It's only about this particular moment. But the residential attractiveness has only one dimension, and it's recently underlined in the literature as well. This is why I distinguished two layers of residential development, residential well-being. The dwelling layer represents the internal platform, such as space, privacy, functional layout, and all that make our internal condition good. And the locality layer is the external residential environment, such as services, access, mobility, and neighborhood functionality. And this distinction is important for me in the context of the study because remote work may affect these two layers differently. It may affect one layer and do not, for instance, affect the other layer. My preliminary assumption was that the remote work directly changes what people need from the dwelling, and it should somehow be reflected in the results. So the home has to absorb work functions and to become a suitable work platform. And from the other hand, remote work doesn't directly create better public transport, better services, better neighborhood, better environment, and so on. So my second question for the study was, does remote work affect dwelling satisfaction and locality satisfactions in the same way? So, and the empirical strategy follows from these two questions. First, I analyzed residential evaluation. If the re-evaluation, if the responders evaluate and re-evaluate their place of living in this particular time is as more attractive, unchanged or less attractive in the time of pandemic. And second, I've tested this dwelling and locality satisfaction split. The residents were asked how, in ordering scale from 1 to 5, they evaluate their current housing conditions. And as predictors, key predictors are used remote work capability, settlement gradient, and two of these predictors combined. So, and this slide gives the full model specification. I will not discuss very well in detail. The important point is the structure M1 together with M1B and test positive revaluation. So in the sense of attractiveness, and M2 checks the other version of the same outcome, and M3 and M4 then separate the dwelling and locality layers. So the models follow the logic of their argument. And this slide provides a full model summary. I included for transparency because this is a very methodologically oriented conference. I will not discuss it in details either, but the substantive argument can be summarized into empirical messages. So first, the positive evaluation was stronger outside the urban core. And the second, remote work was associated with dwelling satisfaction, but not with locality satisfaction. I will show these 2 points more clearly in the next slide. So the first results concern residential re-evaluation, and large cities were used here as references category. And we can see that the odds ratio, the highest odds ratio 7 and 11 is for suburbs of large city, and later gradually we have other type of units, and all of them represent more attractive segments to compare to the large cities. So these differences were adjusted to remote work capability. So the settlement differences remain even after counting whether respondents could work remotely or not. And I will come back just for a minute, for a second, for the model specification. Here we can see that this is the adjusted ratio for the remote work. So altogether, we can say that if we combine the effect of settlement gradient and the effect of remote work capability, the categories that mostly positive reevaluated their home conditions was those who live on suburbs and can work remotely. So this doesn't mean that everyone, of course, wants to leave the city, but the finding is narrower here and precise. So during the pandemic stress test, non-core location were more likely to be positively re-evaluated. So the location trade-off was reweighted. And this is the second finding. I would say the key one for my paper, that the remote work capability is significantly associated with the dwelling satisfaction, but it is not significantly associated with locality satisfaction, and vice versa. So this means that the remote work seems to improve the fit between household needs and the dwelling, but it doesn't resolve the place-based advantages that structural locality well-being. So, in simple words, it doesn't automatically make the neighborhood work better, and even if it makes our home location to feel better. So this is the central argument, and together these results support a layer interpretation. So under home-centered routines, the dwelling become a key functional problem, and it is more sensitive to work regime, whereas locality evaluation is more consistently structured by settlement context. And what is important and what is not presented here, that the locality satisfaction was graduated in the vice versa way. So the most satisfied were those living in big city centers. So the central location and centrality is still the key issues here. And these are several limitations that should be mentioned explicitly. First, this is a cross-sectional study. It's not longitudinal one, so and this does not provide causal effects within personal changes within time. The second one is the timing. So the data was captured in the lockdown moment, so it was not a stabilized post-pandemic situation. It couldn't be applied one-to-one to post-pandemic realities or settlement patterns. And the third is that suburban group was really small, so the results should be interpreted with caution. In the same time, all of the results represented, they were significant. So let's say it keeps the rigor. And the amplification followed directly from the two layers, from two layers results. If remote work increases the importance of dwelling feet, then housing adequacy becomes also more than a private household issue. And space, privacy, and functional layout become part of everyday urban functionality. But the locality results show that good housing is not enough. And suburban and peripheral locations still need services, mobility, and neighborhood infrastructure. And so if we, in our housing policy, we invest only on housing unit, we really under risk to contribute to low service dispersal development. So the policy message is dual. The post-pandemic planning has to address both dwelling adequacy and neighborhood provision, and cannot focus only on housing unit and cannot focus only on neighborhood services. It has to think about both at once. Thank you very much for your attention.
Thank you, Veronica. Are there any questions?
Yes, just a question about the respondents. Yes, because I see that the study was is a national survey.
Yeah.
And you were able to understand the social demographic composition of the respondents?
Yes, we were, because it was, but it has also limitation because it was a quota sampling. So we targeted very particular people.
Okay.
We kept the structure for regions, and we kept the structure for settlement size. So we reflected the proportion is structured at the national level for
Okay.
villages, open rural areas, for large cities, etc. Also, male-female balance was kept, and educational level was kept. So
Okay.
it's and the main limitation was in age, because we studied only working age, which means from 18 till 64. So it's big limitation because we had to skip this elderly category. But there was no way to counteract that because it was released mostly online. And we just couldn't target physically the appropriate sample of elder people.
It's interesting because in your model, maybe it could be interesting to introduce as a variable in the significance also this characteristic, maybe.
Yes, for sure.
Female respondent have significance in one way, and maybe a possible new lecture of the model.
Yeah, thank you. It's for sure. It's an interesting idea. I think I should explore it further, and I should mention that actually it was a lot of questions. It was like 30 questions about residential attractiveness. I've chosen only 3, so it's huge data set, and I'm alone on working on it. Yeah, and looking for collaboration and someone interested.
Thank you.
Thank you.
Thank you.
So I think that Martina is the next, and the contribution on a data-driven framework for psychopath quality, integrating user perception and science.
Okay, good afternoon, everyone. My name is Martina Carra. I am a researcher from the University of Brescia. And today I'm really happy to present on behalf of all these authors, co-authors, our research that is inside of a national project, MOST. I know that Italian people know it. This is the structure of my presentation. So I started to introduce and motivate our study and find some literature gaps, objective and the researcher's composition, because it's a bit complicated. And I will describe the methodology, result, and I finish with a discussion of pros and cons of our research. So a motivation, why we study cycling infrastructure. The motivation is because the cycling is becoming increasingly relevant as a component of the sustainable urban and non-urban mobility, able to improve the climate neutral cities and promote active lifestyle. So several studies approach this topic from different disciplines. So from the transport planning, urban planning, but also very different disciplines like the social science or mechanical engineering. Generally, all of these studies agreed that the good or bad experience of a user, of a cyclist, is shaped by the interplay of several factors that can include the road characteristics, but also the user types, the vehicle types, but also the context, the land use, where the user ride. So is a plan and design a high quality cycling infrastructure is not an easy task. The research contribute with a lot of very interesting results, but we found that some gaps still remains. The first one is that the research have correlated just one or two criteria. So we have different factors that can interact in the comfort, in the quality of this infrastructure, but the research don't correlate, and these correlations are always, or more or less, are always correlated with the engineering characteristics. So the vibration, the correlation with the maintenance of pavement, so the behavior and intersection. The second gap is that all of these this study test this correlation, but the test is performed on simulator that cannot reach the contextually specificity. And the third gap is that all this study focused only in the urban context and in systematic travel. So few studies consider the peri-urban context or non-urban context. And the fourth is connected to the first. The final is connected to the first. So no one focused on the data fusion methodology to interact all of these factors. This is because they correlate just one or two elements. So therefore, we know this gap. The research, the aim of our research was to develop a practical framework able to evaluate the quality of services of cycling infrastructure using real-world data. So the goal was to understand how the physical characteristic, the context characteristic, or the user types, some socioeconomic features of the user or the vehicle types can condition the comfort of the user and try to measure it. For this hard goal, hard, to achieve this objective, we needed to combine several expertise. So the co-authors of this research are you can read it in the slide. Was composed by the three type of expertise. The first one, transport planning, urban planning. I am in the middle because I feel myself in the middle. And the last is Professor Verturi from mechanical and thermal measurement that help us to manage the lecture of the data from devices and sensors. So the methodology we implemented consisted of a 5-step framework, which start firstly with the preliminary activities, and next go to the raw data collection, the data elaboration and fusion. So next we elaborate some the computation of systematic indicators, and finally we apply two different predictive models to find and search to read some correlations. So specifically, in the first step was preliminary activities. So we prepared the setup for the on-the-road trials, and also there are a lot of on-desk activities. For example, all of this work are based on a graph. So we create a graph of the cycle infrastructure, and so with a node link system, and also we segment all of these this structure in a segment of 10 meters to 10 meters to search to merge to this physical representation a microscale data collection. In the second step, we enrich the microscale data set that is composed by two different data sets. The first one was the subjective data. It consists of a structured survey that we administrated to the participant before and after. And the second microscale dataset is composed by several geographic information system layer from spatial, and other data came from a set of sensor and devices. We use a 3-axis accelerometers to capture the vibration of the device. We use eye trackers to monitor the gait behavior is a glasses, normal glasses. We consider methodological station to contextualize the environmental condition like the temperature, the humidity, the weather generally. And bibliometric wearables to record the physiological responses. It was able to monitor the pulse rate, the electrodermal activity of the rider. And finally, we used also a GPS unit to trace the trajectories and the speed of the riders. In the third step, we proceeded with a data elaboration and fusion. We think about this process a lot because we have a lot of problem emerge all of these data sets. So the first step, we remove outlier. In this case, we use the 3 sigma rule for most of the sensor, except for the 3-axis accelerometer, because we have the RMS that is a isonorm that it's able to mitigate the transient peaks. Next, we go to make a temporal alignment, because all these devices have different sampling frequencies. So we try to divide it into a fixed duration time windows in order to synchronize all the devices. And next, we perform a spatial alignment because we want to spatialize this data. We use two different the attributions type. So for the fixed sensor, like the meteorological station, we just merge data from the station to the segment with the nearest station, so in terms of space. And about the mobile sensor, for each duration time window, we compute the vehicle's average GPS position to assign the time windows to a place. So here there is in the slide, is the schema of the temporal and spatial alignment. So we use the temporal alignment of the day, hour, minutes, and second, all of the devices. And next, we have the GPS connected to the three-axial accelerometer. So we were able to correlate spatially all the devices to the spatial DV in quantum Gs. Next, we compute some synthetic indicators because we have a lot of data. Because we have high frequency variables, low frequency data. And next, we implemented two different alternative approaches of predictive modeling. In this case, we approach a traditional approach of econometric approach with a generalized linear regression, and we compare with a machine learning approach of artificial neural networks to see how the predictive models are able to understand the positive negative correlation between the factor and the comfort perceived by the users. So it's not in the paper, but we performed some trials, so I add this result to the presentation. We try this methodology in the city of Brescia. We select 3 different cycle paths. They are very different in terms of segregation, weights, pavement materials, context related. So we are able to compare different situations. For example, this one was in the historic centers with a lot of shared route with the pedestrian, with vehicles. This one was near to the university and industrial area, and this one was a residential area near to a non-urban area, so very near to the mountain of Brescia. Also, we used 2 different devices. We use a traditional bike of the bike sharing of the city of Brescia, Bicimia, and we make some trial also with an electric assist bicycle, also of the Bicimia services, to compare how the device can change the correlation with these factors. We engage 11 users, and we try to have different socio-demographic characteristics to provide an heterogeneous sample of this study. So this is the setup. This is Stefano Raccagni, our PhD student, the co-author of this paper. Okay, this is the setup. We have the bibliometric data is a watch, so it's weird, and the eye tracker is a glass. Also, we placed 2 3-axis accelerometers, one in the sandal and one in the handlebars, because it's the most critical points for the vibration. And next, these 3-axis accelerometers are connected to a GPS. This is in the back. This is the result of the step 2. This is some geographic information system elaboration of several contextual and road characteristic features. For example, the slope, the building density, the building age. So all of these factors are correlated to the segments. We take this data from national and regional geoportals, from WebGIS platform, also from collaborative mapping projects of other research, and also in field audit for some of this. The data don't exist. The subjective data, as I said before, was performed with a structured questionnaire. In this case, we collect the socio-demographic data, the daily behavior about cycling of the user, and also we ask to them, obviously, the comfort they perceived during the cycling in terms of safety, fatigues, environmental quality, and they express it with a Likert scale from 1 to 5. And also, we integrate a map. So the participant was able to contextualize bad or good points about several features of the run. Next, of the data collection, we perform data elaboration and fusion. About the outlier removal and the temporal alignment, we perform it with MATLAB because there is a lot of data in Excel. It's impossible. And next, we use geographic information system, specifically quantum GIS, for the spatial alignment and also for the data fusion, because the instrument was very useful to understand spatially all this data and merge. We consider more than 80 indicators that we put in a unique database, and we calculate sensitivity indicators. Next, in the last phase, we apply predictive modeling. There is the result here of the econometric approach, and here in the machine learning approach. The interesting thing is that 34 factors resulted as significant. So it's true, there is a lot of factors that are significant in the cycle quality of the infrastructure. And also an interesting thing is that the significance of these predictors are more or less the same in the two models. And if we compare this result, we can see also that the comfort booster or the uncomfort factors are more or less similar in the two methods, in the two approaches. The only thing that is a little bit different is that the machine learning approach have a lower error in the prediction. And so the comfort booster a lot, for example, the bikes help in the comfort of the user, the paymentation, the maintaining payments, the presence of bidirectional cycle infrastructure, or, for example, the presence of trees and greenery. Also, the discomfort factor consider the vibration, the humidity, the long ride. So, more longer is the ride, the worse is the comfort, and the presence of a cycle path in the industrial area, and also the wind, because it increases the fatigue. So this result can be useful to understand and make maybe an assessment, an index of the cycle path, inform the policy, inform the planning, how to make this infrastructure, or also to program the maintenance. And to conclude, we want to transform this data in order to identify an index of quality, so the quality of service of this infrastructure, but we need to improve the next step. And we know that we have some pros and cons in this research. The first is that segment-based representation was very useful because you are able to understand where there are problems, where there are some discontinuities, and so you are able to spatialize the user perceived experience. The second is that the integration of subjective and objective measurement improve the validity of the assessment, because always we consider only objective, no objective measurement. And from a modeling perspective, we see that we have a complementary benefit between the two approaches. But I want to highlight a things. We use this predictive model not to predict something. I'm not really in confidence with that prediction mode, but just to help the diagnosis. Help if there are linear or non-linear correlation between the factors. Obviously, we have several problems and negative points because the method is complicated. You need to collect all this data. You need to have a lot of devices, a lot of sensors. So in fact, we make one trial at a time. So it's hard. We need to expand the trial because we need to understand with other users, different contexts, how this factor works. And also, especially in the non-urban travel, because a systematic travel are, I think, an emerging market, very, very interesting. We want to test it. Okay, this is the reference, and thank you very much.
Thank you, Martina, for your presentation. And from the audience, anyone questions?
Yes, in this case of the experimentation, do you use a very complicated device? But do you imagine in the second phase of steps of this research, do you think it is possible to use a more simple device? I imagine for the use of bike sharing, it's necessary the smartphone to unlock.
Yes.
The fact, do you think it's possible to reduce the number of the information that you collect in the first step, in the second step, and we will use only the data probably are available by the smartphone? Or...
Yes, I think not all, but most of all, because for example, no, the app for the healthy app have a lot of measurement of some biometrics factors. Also the GPS, also the I think the XY axis, but I think not the vertical ones. But I think that the most complicated is the eye tracker.
Yeah.
Because in the glass you have a sensor that measures the fixation, the direction of the fixation. So it's really complicated, and it's very interesting because I wanted to integrate it and see if with the epsilon and x-axis it's possible to correlate the orientation of the view. So see what contexts are more viewed and reach the. I think that is this is the problem, and also the privacy concern. Because for this study we are now we are discussing with the ethics committee of the university because it's correct, but it's not easy. Okay, thank you very much.
Thank you again, Martina. And we will come to the last presentation. I think online we have Carmen for the contribution of urban data-driven energy planning, insights and challenges from Italy and Portugal. So, Carmen.
Hi everyone, can you hear me properly?
Yes. Please.
Okay, I'm sharing my screen to start presenting. Okay. Good afternoon, everybody. It's a pity not to be with you in Braga. I'm presenting this contribution titled Urban Data-Driven Energy Planning, Insights and Challenges from Italy and Portugal, also on behalf of the co-authors of this contribution, Gerardo Carpentieri from University of Naples, Federico II. We are from the same laboratory research team, and Paolo Ricardo Batista from University of Aveiro. This research comes actually from a tentative attempt to develop together a joint research because we had two datasets concerning energy consumption for the two cities, Naples and Porto. We were very interested in finding out which urban characteristics were driving the energy consumption in the two cities. But once we actually compared the workflow on the construction of the databases, we realized that we had to take a step back, and we realized that the interesting result was still in the in how we had to manage energy consumption data to better develop decision support tools for policymakers. Energy nowadays plays a vital role in sustaining the metabolism of cities. In a linear urban metabolism, energy is also responsible for most of the emissions in urban environment. And looking towards a more circular urban metabolism, saving energy is essential to limit the amount of waste, organic and inorganic, due to the emissions and the burn of non-renewable energy within urban environment. Also, due to the energy crisis we are living recently in the recent years, due to geopolitical issues, energy vulnerability has increasingly been a central issue to urban quality of life research. But dealing with energy data also implies the need to go further and to get to have some fine-grained data in order to avoid the citywide average that may hide neighborhood-level disparities. But fine-grained spatial data is needed to target intervention effectively and to avoid the approach of one-size-fits-all solutions. But looking to the panorama, to the landscape of energy datasets across Europe, there are two very different and common approaches. One is to deal with two fragmented user-level, but spatially noise and hard to integrate energy datasets. This is mainly due to the fact that we have two different actors actually deal in creating this kind of energy dataset. There can be many fine-grained, so very detailed, but the fact that they're created by different actors and also for different purposes, ranging from tax agency, municipality, and main energy actor, they end up to be very fragmented and especially inconsistent. On the other side, we have two general data, energy data. They may come from national portal and they may integrate aggregated energy consumption datasets, or regional data, sometimes from metropolitan area, or when you're lucky to major city data. So the research question we asked ourselves before getting into developing a joint model to address the urban characteristics that mainly affect energy consumption in Naples and in Porto, we asked ourselves, how does the structure of available energy data, so user level versus aggregated dataset, shape the choice of spatial methods? And the second research question actually concerns under what conditions can indicators from different data infrastructure be validly compared across cities in that cases. So we actually developed a comparative methodological framework. On one side, the user-level noise and spatially inconsistent records from our case studies, where a geocoding approaches was needed in order to clean up and also make the dataset more spatially relevant. While on the other side, the methodology of disaggregating data, so starting from aggregated data, cleaning records in order to have somehow a consistent data set still spatially, in order to find ourselves in the ideal target, so the highest resolutions in order to develop urban targeted data, and also the highest standardization in order to make these kind of methodology also somehow replicable. So to develop our methodology, we considered two case studies. So one is Naples, a city of about 1 million residents, whose dataset was made of energy dataset was retrieved from Seattle and the Italian Revenue Agency. It consists for the 2021 of more than 500,000 records that actually collected energy consumption, yearly energy consumption per each user of the city. Here, the challenge is quite clear. We had to pre-text billing addresses that we need to put on the ground to find their points and geocoding on the ground on QGIS, which was, of course, in contrast with cartographic standards. So the challenge here was the noise and the spatial inconsistency of the dataset. On the other side, we had Porto, where actually we had to apply a disaggregation approach. In that case, the data source were national, so high standards in terms of standardization, but resolution was very poor, since Porto was divided into CP7 postcode level. So the input data in that case was aggregated by postcode level, which was still more than a neighborhood, so was not necessary, it was not useful for the ideal methodology and investigating which urban characteristics were driving energy consumption. So the challenge here was a standardization, of course, that requires the translation of aggregated data to census tract from the BGRI 2021. So we developed two parallel methodologies, one for Naples they actually were developed on two different parallel ways, going from two different directions. The first one from Naples has a first stage where an automated cleaning and matching was needed. We started from our input data, so the Seattle raw dataset, that contain, as I mentioned, about 500,000 records from energy consumption. This dataset was first cleaned using machine learning algorithm of information that were not useful for our case, so floors, stairs, and whatever was not meant to be relevant for the analysis. On the other side, the input file was the strict directory for the city of Naples, so the name of streets and squares and little streets and neighborhoods that we used to create a FATSI match algorithm with the cleaned, at least at first cleaning the dataset. This FATSI match resulted in a score. If the score was higher than 95%, the row, the record, ended into a geocoded dataset. In case it wasn't, actually a further step was needed, occurring through an operator review in order to identify a recurring pattern and populate a correction vocabulary that we used to actually replicate stage one, so rerun the FATSI match algorithm using the correction vocabulary, so to actually include also the street directory into this new FATSI match. In case the score was positive, the data were included into the geocoded dataset. In case it was not, we had to recall to a software online, a GeoPify fallback for residual unmatched address. The geocoded dataset, once the information about the latitude and longitude were needed, it was possible to create the tract level energy consumption data. On the other side, so for the Porto, we had to start from the Polygon CP7 interface, so polygons actually around administrative postal codes that we managed to clip using address and postal inputs in order to merge keys and create a cancellation and clipping algorithm in order to have at least a first cleaning of these data around address and door points. The second step has an input to the building data from census, from national portals. We managed to create two series of data, one weighted by the area, so the footprint of building, another one weighted by volume, so footprint plus the height, the elevation of building. So two parallel series, one energy weighted, area weighted, and another one weighted by volumes. So the output is then the creation of an indicator family, considering population, household, and floor area, different data according to our energy consumption, according to area or volume. And in that case, it was possible to get then the information to tract level energy consumption dataset. Looking to the results for Naples, so starting from the 500,000 records we started, we had the chance to get to 93% of successfully geocoded records with a clear spatial pattern, so highest concentration in dense historic hillside districts, lower in peripheral areas. We used an hexagonal grid in that case because of the consistency with the tracked units. It was a choice made about resolutions and to use the resolutions we were able to get. This is instead the results get from the Porto side. So from postal code energy dataset, dataset about energy consumption at the census tract. In that case, we do not have a successful rate since it was not possible to compare with the actual energy consumption, but actually the two series of data, the energy obtained by weighting area and the other one compared with volumes, actually cause a 12% average variance in tract estimates. So here's the synthesis of these comparative results. The starting point were two different sides, as I mentioned, one going to the, starting from very noisy and inconsistent data. The other one was aggregated and still inconsistent data from the spatial point of view. And two success rate sensitivity. For Naples, 3% of geocoded records. On the other side, taking into account the 12% of variance among the two tested weighting algorithms. And then resulting spatial unit for the Naples case study, a 100-meter hexagonal grid, on the other side, census tract that can be, of course, compared also in that case. Both maps successfully reveal, in conclusion, strong intra-urban heterogeneity. Actually proving the hypothesis as the basis of my speech that citywide averages are proven insufficient for planning. But for Naples, we have observed the residential demand, so the actual energy consumption of users within the city. On the other side, we have modeled the mixed low voltage demand got from observed demand aggregated at postal code level. A shared unit level, so in that case, kilowatt hour per household, is necessary but not sufficient for a valid comparison. Also, when we turn to getting more into the detail about the urban characteristics driving the energy differences among the city itself. And to conclude, the main takeaway we wanted to stress with our presentation is that even when delving with the same kind of data, so same cities, different cities, but same data set and same research question, it is necessary to know the unknowns, so to stress which of the variables we have to deal with are somehow under our control and which is actually not under our control. In the Naples case, it's still a 7% of geocoding resistance. For Porto, it's the difference between the two models. So it's something to keep in mind also when deciding which data series to consider. In the case of Naples, it is a kind of stochastic noise. Errors were proved to be randomly distributed, so ensuring that the spatial signal of the resulting of the residual not geocoded data are kind of hotspot, not statistically representative. While for the Porto case, uncertainty here is not noise, but a reflection of the disaggregation of data towards a more spatially consistent result. So actually, the conclusion of this work and what we actually would like to bring with us also in developing first steps of this research is to take into account that transferability research must prioritize analytical equivalence, even if we have to somehow name the same variable. These pipelines also have been designed to transfer administrative noise or something that can be translated into actionable data, into intelligence, into knowledge for the development of sustainable energy and climate action plans, no matter which condition the city needs to face, if too noisy and inconsistent data or too aggregated data. And the future work actually include the finalization on social normalization tracks and documentation of residual geocoding uncertainty in order to have 100% of geocoded data on one side and on the other, at least know what brings the difference, the variance between the data on the other side. Thank you.
So thank you, Carmen, for your presentation. It was very interesting. And I don't know if there are any questions from the audience. Yes, maybe you can, if you can come here, we will hear you better. And you have a question from Martina.
Hello, Carmen. A curiosity. Because you calculate the energy consumption in terms of household. The question is, this data concern or not also the public facilities or commercial facilities? But because in urban area maybe can change the result.
Yeah, I may have missed this information at the very beginning, that both the two data sets were referred only to residential consumptions. So we used household as a common denominator to get more into the energy consumption and to their trends within the city itself. So actually, also in that case, we can further discuss that maybe some errors and some noise may be relevant, especially for the Naples case study. But actually, to do data set comes only for residential units. So they should be only for residential units, so only households.
Okay, thank you very much.
If aren't any questions, thank you again, Carmen, for your presentation. And I think we actually ended on time, so we were quite. So I think I thank you all for the participation and presentations, and we will go to the coffee break. I'm sorry, Carmen, you.
Enjoy it for me as well. I know you have also a very interesting trip soon after the conference sessions.
Right. Thank you again. Thank you all. Bye.
Bye, bye, thank you.
Caffè.
Poteva essere un suggerimento.
Hi, I'm Vincenza Torrisi. I'm the chair for this section. Is there someone in the room?
Good afternoon. I am Giulia Biondi, and I will be the technical assistant for this session.
Hi.
For any problem, please refer to me. Thank you. I guess, Vincenzo, you are going to be the chair for the session?
Yes. Before I asked if someone was here. Okay, perfect. Yes, I will chair this section. Maybe there is also another section, another chair in the program, but I don't know.
Yeah, I can hear you. Sorry, it was my problem.
So I start just to ask if we have all presenters or in the room, but we are all virtual, I saw in the program. So for the first and the second presentation, since I am one of the co-authors, I can confirm that we are all here with my colleagues. Then we have other three presentations. So I have Alicia, Germania, and Andrade Vera. Is there someone connected with us? No. Then we have another work titled Deep Learning Based Acoustic Event Detection in IoT Edge Devices.
Looks like there's still no one for that.
But and for the third one, before I mention just the author, the title is a Secure Microservices Architecture for ICC Top Cybersecurity Applied to a Graph-Based Curricular Analytics Systems. And then we have the last one. The title is Lightweight Side Channel Resistant Through Random Number Generator Design for FPGA-based Edge AI Platforms. No.
And the speaker seems to be connected, actually. It's Kiao Pam.
Kiao Pam is the last.
Who seems to be online. Yeah.
Okay, so he's with us, but we don't have the third and fourth presenters. So maybe we can wait just a few minutes, then we will start with the first, with the second. We will see if someone come, otherwise we skip and we move to the last presentation, and then we wait for the others. Okay.
Yes.
Okay. I start to share the screen for the first presentation. So you can confirm. Okay. Okay, perfect. So I introduce the first presentation, which is titled Configurational Accessibility and Mobility Pattern in a Port City Interface, a Space Syntax Analysis of Central Catania. This is a joint work with my colleagues from University of Catania, but I leave the floor to Sheila Bellia, our PhD students, who will introduce us and also will explain the main finding of our work. Okay. Thank you, Sheila.
Thank you, Professor Teresi. And good afternoon to everyone. I'm Sheila Bellia and I'm a PhD student from the University of Catania. And today I have the pleasure to present this work developed in collaboration with Professor Vincenzo Torrisi, Reza Scarizad, Professor Matteo Ignaccolo and Professor Chiara Garau. Before we move into the core of our research, I would like to briefly outline the roadmap for today's presentation. We have structured our work into 5 main sections. Introduction, we will begin with addressing the complex challenges inherent in the port city interface and define our primary research aim, so understanding how spatial configuration relates to movement dynamics. The methodological approach, I will walk you through our methodology, which combines space syntax analysis with empirical data collection. Case study, we will zoom in on a specific context of Catania, analyzing the territorial framework and the mobility issues it faces, and the results. This will lead us to our findings, where we will examine the configurational mappings, the correlation between spatial structure and empirical flows, and a comparative look at pedestrians versus vehicular patterns. Our research starts from a fundamental observation. We have transitioned from a historical area of functional synergy to a modern state of friction, and these port areas, once the lifeblood of urban growth, have become zones on physical fragmentation and social-spatial disconnection. We are looking at 3 specific challenges here. The first is accessibility barriers. The expansions of logistics infrastructure often reduce permeability, acting as a physical wall that isolates the waterfront from the daily life of the city. The second is the functional conflicts. We face a clash of logistical operations versus urban activities, and they coexist, but they collaborate, which leads to inefficiencies in both trade and urban livability. And finally, the opportunity. This is not just a problem, but is a regeneration challenge. We believe that waterfronts should act as transitional spaces, and the goal of our work is to determine how to integrate planning strategies to balance port efficiency with the needs to of the urban population. To address these challenges, we need a way to measure this disconnect, which led us directly to the methodology we employed. So, what is the core objective of this study? As you can see in this slide, our research follows a clear methodological path designed to bridge the gap between a theoretical spatial configuration and actual real-world movement. We don't just rely on one perspective. Our work is structured around 4 key steps. First, we apply space syntax to quantify structural accessibility, focusing on parameters like connectivity, integration, and choice. Then we move to the field to monitor real-world mobility, collecting empirical data on pedestrian and vehicular flows through the gate counts technique. And the heart of our research lies in the third step, cross-referencing our findings. By comparing our theoretical spatial model with actual observed flows, we can assess the structural alignment or misalignment of the area. And our final goal is to provide an evidence-based insight that can guide sustainable, accessibility-oriented urban planning. To analyze these per-city challenges, we needed a framework, and we adopted space syntax, which allow us to move beyond seeing the city as just a collection of streets and instead interpret it as an integrated system of spatial relations. Our approach is grounded in how people actually navigate urban environments. And the research shows that both pedestrians and drivers tend to follow paths that minimize angular changes and reducing their cognitive load. We reflect this by modeling the street network as a system of interconnected axle lines. And as shown here, we quantify this configuration using 4 key measures. Connectivity, which gives us a local snapshot of immediate permeability. Integration, which tells us how central or segregated a space is within the global system. Choice, which highlights the streets most likely to be used for through movement, and intelligibility, which measures how readable and navigable the environment is, based on the correlation between local and global properties. This quantitative data forms the foundation of our analysis, and however, a model is only as good as the reality it represents, which is why we combined these with empirical gate counts to measure actual movement patterns on the ground. Moving from the theoretical model to the fields, this slide outlines our empirical data collection process. And to quantify actual movement dynamics, we adopted the gate counts technique. This methodology allowed us to collect empirical data on both pedestrian and vehicular movement, ensuring a direct comparison between observed flows and the syntactic properties of the street network. Our approach was structured in 3 ways. The gate count technique, we use this consolidated methodology to measure traffic density and volumes within the urban space. Stratified approach, we selected strategic monitoring points, the gates, C1, C2, C3, and C4 along Via Dusmet, and these were chosen to represent different spatial conditions, specifically intercepting urban circulation, port access, and the influence of transport hubs. Differentiated monitoring, we recorded pedestrians and vehicular flows separately under comparable conditions. This was essential to explore how spatial configuration influences these 2 distinct movement patterns. And this empirical basis is what allows us to verify the consistency of our syntactic model with actual movement patterns. Now let's apply this methodology to our case study, the port city interface of Catania. As you can see, our analysis focuses on a strategic transit zone connecting the historic city center to the tourist port. While Catania covers a wide metropolitan area, this specific sector is a critical hub where urban, tourist, and port-related flows converge. This area is under a significant pressure from both residents and commuters from hinterland, and several key factors characterize this site. The area acts as a crucial link between the historic urban fabric, the port basin, and the major regional mobility actors, such as the central railway stations. Despite the presence of public transport infrastructure, including rail and bus services, the area is still dominated by private vehicle use, which often leads to road network saturation and congestion. We must manage the coexistence of daily urban activity, logistics related to the port, and the tourist-related points of interest, such as yachting activities. This context provides the ideal setting to test whether the spatial configuration of the streets network, specifically in corridors like Via Dusmet, aligns with the actual distribution of movement we observed on the ground. To ground our analysis, we identified specific monitoring section within our study area, as shown in the image. We selected 4 strategic sections along Via Dusmet, identified here as gates, to serve as our primary data collection points. These locations were chosen with a specific purpose, because they intercept a variety of movement conditions inherent to the port city interface, including access-related traffic, general urban circulation, and the influence of nearby transport nodes and bus services operating in the area. By positioning our gates this way, we ensured that our empirical basis captures the morphological and functional heterogeneity of the study area, and also this allowed us to compare our syntactical spatial hierarchy with the actual traffic dynamics observed on the ground. Now let's look at the results of configurational mapping, starting with the connectivity analysis shown in the slide. This map reveals the local hierarchical structure of the urban fabric based on direct intersection, which we use a measure of local permeability. What immediately stands out is a deep red axis, that is Via Vittorio Emanuele II, which records the highest connectivity in the study area. And as this main artery, it plays a critical role in distributing flows between the upper part of the city and the waterfront. We also observe another peak of connectivity at Duomo Square, highlighted as the detail 2 in the slide. The street grid clearly converges toward this public space, making it a fundamental distribution node for both pedestrians and vehicles. Lastly, our key finding here is that the spatial structure supports the city's monumental hierarchy, and the Cathedral of the Duomo serve not just as a tourist destination, but as a central hubs that are deeply integrated into the local network, facilitating the overall permeability of the historic center. Moving on to the choice attribute shown, this measure helps us to understand the through movement potential of each street within the system. Essentially, it identifies the street most likely to be selected as the shortest part between different origins and destination. And as you can see in the map, there is a single prominent deep red line, and this corresponds to Via Vittorio Emanuele II. Our findings indicate that this axis concentrates the vast majority of the through movement potential for the entire network because of its strategic position and linearity. This route functions as the primary movement channel. In contrast, the surrounding streets shown in blue play a strictly local role, emphasizing how critical this single corridor is for mobility across the fabric. Next, we move to integration, which measures global accessibility. As shown in the image, this parameter tells us how topologically close a street is to all other streets in the system. And the most prominent feature is the long horizontal axis of Via Vittorio Emanuele II, marked as detail 1. This road acts as a global collector and effectively concentrating movement and reducing the topological effort required to navigate the neighborhood. Furthermore, the integration core expands with peak values at Paolo Borsellino Square, shown as the detail 2, and this node is not a transit point, but a central configurational element of the system. Its strategic position makes it the main accessibility core for movement between the tourist port and historic center, confirming its role as a key transition point in the urban fabric. Beyond the individual measures of connectivity integration, we assessed the intelligibility of the urban fabric as shown. This parameter represents the degree to which a user can understand the global structure of the city based on local visual cues. And mathematically, it is expressed as the statistical correlation between connectivity and global integration. And in the context of an organic and historical urban fabric like Catania, this is a moderate yet expected value, which is squared R 0.25. While the system is not as immediately readable as a regular grid, is still recognizable configurational logic, and the streets with an higher local connectivity tend to occupy more central positions within the network. In essence, this confirms that even in complex history environments, there is an underlying legibility that helps users to perceive their position within the heart of the system. Now let's look at the actual movement dynamics we recorded in the field, which are summarized in the slide. The data highlights a clear hierarchical differentiation between our monitoring gates. And for example, for pedestrian concentration, we observed that pedestrian flows are strongly concentrated towards the northern sector of the area. Specifically, gate C1 acts as the main pedestrian actor with 171 pedestrians per hour. The vehicular patterns emphasize the transit role of our perimeter roads, and gates C2 and C4 handle massive volumes exceeding 2,000 vehicles per hour, which is consistent with their strategic role in port access and traffic distribution. Interestingly, we noted a functional divergence at gate C1. Despite its prominence for pedestrians, it records a lower vehicular volumes, 882 vehicles, suggesting its role is more closely related to local distribution rather than the measure of through traffic. We now arrive at the core of our research, verifying whether our theoretical model aligns with reality. And let's start by looking at the pedestrian patterns, which are summarized in the slide. The data reveals a very clear positive trend, showing a strong correlation between the syntactic values we calculated and the pedestrians' volumes we recorded in the field. In particular, the relationship between pedestrians' flow and the choice parameter is remarkable, showing also a perfect linear correspondence with the squared R. Similarly, both connectivity and global integration show a substantial association with pedestrians' presence, which confirms that our spatial network is far from a passive element. The implication of these results is significant. The physical configuration of the streets network is not arbitrary, but effectively guides pedestrians' flows toward the city's monumental core. For pedestrians, the syntax of space proves to be a reliable indicator for predicting how people choose to move through this urban context. In stark contrast to the pedestrians' results, when we look at vehicular patterns shown here in the slide, the relationship with our spatial model change completely. As the plots demonstrate, the correlation between the vehicular flows and our syntactic measures is weak and less coherent. Specifically, the relationship with a global integration and local connectivity is extremely weak, and even the association with choice remains limited. The implication of this finding is fundamental to our study because vehicular movement is not driven by the intrinsic configurational logic of the urban grid. Instead, it is primarily influenced by the external function factors such as port-related access and specific traffic regulations. This highlights a clear functional divergence in how different users experience the port-city interface, proving that the street network's layout guides pedestrians far more effectively than the vehicular circulation. To wrap up, our research into the port-city interface of Catania has revealed a fundamental divergence in movement patterns. Our findings have shown that pedestrians' mobility aligns closely with the spatial structure of the urban grid, confirming that configurational accessibility successfully supports walkability. In contrast, we found that vehicular mobility is driven primarily by operational and functional constraints, such as port access and traffic regulations, which often override the natural hierarchy of the urban network. This mismatch points towards two distinct strategies for urban policies. For pedestrians, we believe we should build upon the existing spatial logic by reinforcing walkability, improving, for example, sidewalk quality, and implementing wayfinding systems along the city's most integrated axis. For vehicular traffic, however, management strategies cannot rely on urban form alone. Instead, we need measures like traffic calming, selective access control, and the redistribution of port-related operational functions to reduce, for example, pressure on the urban fabric. Finally, we recognize that our study is exploratory and context-specific, and future research should aim to strengthen this empirical basis by increasing the number of monitoring gates and the extending observation across different time periods. Furthermore, we intend to integrate multimodal data, including public transport and micromobility flows, to support more evidence-based planning strategies for the future of our port-city interface. Thank you very much for your attention.
Okay. Thank you, Sheila, so much. Are there any questions? Maybe someone joined us, I think. Yes, because now I can see Chiara, Anthony, they weren't before with us. Okay. Are there any questions? Otherwise, since I am one of the co-authors, I already really would know the presentation. I would like to thank Professor Chiara Garau, which is one of the organizers of this conference, because we developed this work jointly with Chiara and also one of her researchers, because it was framed within a PhD course developed by Chiara, and for which Sheila had the possibility to follow and apply, implement the different tools for urban planning, for transport management systems, and so this is one of the applications to our city, so the city of Catania, as Sheila showed in her slides. So now, Giulio, can you confirm that you are listening us well, that the connection is good?
Absolutely, it's working perfectly.
Perfect.
And we can still see the break time page while we are not sharing, so I asked the management to turn it off. But meanwhile, you can just go and share your screen.
Yes, okay. I will share the screen for the second presentation. One moment, please. Okay. Okay. I share again the screen. Okay, perfect. So now we will introduce our second work. I'm here with, I think that then I will move from the camera with Ezio Riggi, one of our colleagues. This is a jointly work with Sheila Bellia, which presented the work before, Professor Matteo Vignaccolo, we are all from the University of Catania, and our colleagues from the National Research Council, Ezio Riggi, Giovanni Avola, Alessandro Zaldei, and Miriam Di Stefano. Today I will just introduce the background of our work, the main aim, and why we decided to move beyond this research. which focus on a digital twin-oriented monitoring framework for traffic-related environmental hotspots and future nature-based solution in Catania. And then I will leave the floor to Ezio Riggi to show the results, the application of our methodological approach to our case study. So, I will discuss in the introduction about the current urban challenges, which ask us to develop an integrated sensing, and this is our specific research objectives. Then we will move to the background and the project framework. We will analyze what we consider as urban intelligence paradigm. We will focus on the potential of digital twin, and I will give you just some quick information about the WISH pilot architecture, which is the big project within we are developing our research. So we present just a part of our research for this project architecture. Then my colleague will describe the study area and the monitoring design. He will detail the context of Catania and our approach to multi-source sensor placement in order to evaluate the effect of nature-based solution. Then we will identify the environmental hotspot analysis in order to demonstrate the identification of traffic-related hotspots and the potential assessment of future nature-based intervention. And finally, we will discuss our findings and provide some conclusion and further research. So, just to better understand what is the motivation behind our work, we just first look about the challenges that currently our cities are facing. So, in modern urban systems, we can experiment the pressure from vehicular traffic, but also air pollution and climate-related factors. And especially in our case study, Catania, which is located in the Mediterranean context, these challenges are amplified because we are with the dense building fabrics, with a limited natural ventilation, and also we have a higher solar exposure. So we don't have just simple logistical or technical issues, but they carry significant public health implications. We know what are the impacts of the exposure to NO2 and particulate matter for health and cardiovascular risks. So, furthermore, we are facing also the intensification of the urban heat island effect, which is characterized by frequently heat waves. So, the core problem is that traditionally the issues related to mobility, environmental quality, but also the mitigation of this problem was addressed by separate and siloed approaches. And we know that this fragmentation often limits the ability to plan effective intervention. So, in this regards, our research aims to overcome fill this gap by moving towards an integrated framework in which we consider together the urban stress as a systematic outcomes of spatial and functional organization. So this brings us to the core motivation of our work, the necessity of integration. So currently, the urban management is considered, as I said before, as a siloed approaches, where mobility, environmental quality, and infrastructure are considered as a separate domains. But to move beyond, we are trying to propose a systematic interpretation of the city. We want to recognize that traffic dynamics, but also environmental condition and health of green infrastructure are not independently. We can consider these as layers that mutually interacting between them as a complex urban system. So our research is dedicated to bridging the operational gap. And this is linked to the concept of, to the high-level conceptual digital twin architecture that is based on real-world monitoring. So our framework is designed to close this divide in order to create an operational chain where sensing, but also data integration and decision support are linked in order to transform the raw observation in actionable urban knowledge. So, building upon the challenges, our research is driven by 4 primary objectives. So we have the formalization of a monitoring framework where we try to establish a methodological and operational basis characterized by multi-source urban monitoring. Then we identify the hotspot in order to support the relationship between traffic and environmental issues. This is useful in order to assess network-based solution implementation and enable finally digital twin development in order to give this real-time traffic and environmental monitoring, and also to support evidence-based governance. So the theoretical foundation of our research find its core inside the project, the urban intelligence paradigm. So the project is called WISH. We want to make a reinterpretation of the city as a complex system where we see the interaction between different subsystems. Within this framework, considering mobility, environmental quality, and also the infrastructural, we consider them as a layer inside an interoperable digital twin. So this represents the crucial strategic shift in our approach. So we move from the traditional sector-specific data management to a more holistic and evidence-based planning model in order to support adaptive governance and more strategic integrated urban planning. So we just quickly focus on the concept of digital twin because as I told before, one of the most important aspects of digital twin is characterized by the representation of the system, characterized by the integration of not static data but real-time data in order to support both the environmental and urban planning. So we want to generate with the digital twin a real actionable knowledge. So our framework is designed to transform heterogeneous real-time sensing data. So this is one of the most important concepts for a digital twin into operational insights, which are essential, of course, for evidence-based planning and adaptive governance. So finally, our approach relies on a system of systems logic. So this enables the interoperability between different thematic layers, so such as the digital twin of mobility, and the digital twin of air quality. So by facilitating this interaction, we can interpret how, for example, traffic pressures translate into localized environmental impacts, moving away from the fragmented interpretation to a unified analytical structure. So this is the architecture for the WISH project, which is, as I said before, characterized, I just reported the two digital twin layer for which we are involved. So the digital twin for mobility, DTMob on the left, which analyze vehicular and pedestrian dynamics, and the digital twin of air quality, which integrates atmospheric measurements with urban context information. We try to perform a unified environment with centralized data lake enabling data interoperability, and this constitutes an operational workflow for the digital twin. But I think that now, from the next slide, my colleagues Ezio Riggi will show you more interesting evidence of our work. So many thanks in advance, Ezio.
Thank you, Professor Torrisi. I hope I can give you something more interesting about the project and the approach we are going to put in order in this activity. My name is Ezio Riggi. I am a researcher and I act as an agronomist and as the responsible of the CNR unit that is established in the Catania area. That is obviously the main area for the WISH project. ENSA just gave us some information about Catania. Catania is characterized by some specific aspects related, for example, about the number of people living in Catania, that is about 300,000 people, but they became about 500,000, including also functional population. But one of the aspects that we have to take in account when we speak about the air quality in Catania is the presence of our mother Etna, that is the tallest active volcano in Europe, and many times is also active in terms of pollution, just because, for example, for particulate matter, the main part of particulate arrives from ash, derived directly from this aspect, and from this natural part of our ambient. Catania is also characterized by a story of the wind that is not so affecting the distribution of the air, and so is more regulated by the presence of a large coastal area. And all these aspects influence, together with the traffic and the presence of some part of industrial still active in the area of Catania, that influence obviously the quality of the air. Just for this reason, we try to develop two experimental kind of approach, just to evaluate the effect of nature-based solutions on air quality, but also, as said by ENSA, on the effect that can be experienced by the heat waves that sometimes, and so many times in these last years, are experiencing for all the Europe. And so we are concentrating on two different kind of experimental design. This design I'll express in the next slide, and so now I show you the main kind of instruments that are sensor that our institute, the Institute of Bioeconomy of National Research Council, projected and also developed and built and used in many parts of the world. They are the sensor just giving us many information simultaneously, measuring particulate matter, nitrogen dioxide, ozone, carbon monoxide, temperature and humidity. all these variables are collected together and are also related to temperature, air temperature, and air humidity. We also use, we can use also some of these kind of sensors just to connect and have also information about agronomic aspects. I am an agronomist, and so I'm sorry, but I think always also to these kind of variables. But in the project, in the WISH project, we use this specific kind of sensors just to evaluate the influence of the tree and the tree development on air temperature under the area covered by the tree. The first experimental area is the Falcone Fama site, that is a representative traffic hotspot in the city. And our experiment design compares measurement collected simultaneously in different environmental conditions. As shown by the arrow, one of the areas in which we put our instruments is close by the main way where the traffic produce pollution. And we also measure simultaneously in other 2 points, in which one of these points is just covered by the presence of a natural park with adult tree plants with different species, and another area in front of the area protected by the park that is actually used by a parking area with some specific kind of structure, including limited area with trees, and so it can be useful also to control the response of air distribution of respect to the part where the pollution is generated. As shown in the area within the parking area, we also installed some sensor to measure wind in terms of direction and speed, just to have also an idea about the movement of air in the area. The data are starting to be collected from the last part of April, and so in our presentation we are not showing results of the trial, but just presenting the experimental design, and these are the first data we are collecting. Another experimental area, the second experimental area, sites, is connected about an area close by the international airport of Catania, but in this case our interest is connected to the presence in this parking, still a parking, where we have many different kinds of trees. And so we want to compare different tree species growing under similar environmental conditions. And so this is a true experimental design. And the objective is not only identifying which species reduce air temperature more effectively, but also providing scientific evidence that can support future urban greening strategies. This is our kind of installation in which the instruments where temperature is collected is connected to a specific sensor that go under the shadowed area. And just because the plant influence in terms of shadow, but also in terms of transpiration, and so different species can produce different effect on air temperature, we want to test and we want to measure directly this effect. The last, but the second major activity of the project is the development of a truly multi-source environmental monitoring platform. And in this case, we combine 5 fixed monitoring stations with 13 mobile sensing units. Some of mobile sensors are installed on public bus, while others are carried during the dedicated monitoring campaigns by pedestrians. This effect, which I'll show better in the next slides, make us able to have a very wide measuring idea about the data of air pollution in a wider area respect the typical standard fixed position sensors. And this represents one of the most important parts of our efforts. For this reason, I move directly to the next slides, in which we summarize the core of our air quality monitoring framework. As first, I want to make you concentrate about the map in which you can see the grid we prepared. The grid is connected to one level of our multi-source measuring system because the grid and the specific centroids and the dimension of each shell is derived from a model built with the data from Sentinel-5. But we adopt the same grid also for measuring data from the ground, from sensor installed on bus and used by pedestrians. For this reason, our system involved in his complete system a first level connected to satellites and reanalysis products such as Sentinel-5P and CAMS that provide data directly measured by satellite and by system of Copernicus system, giving us an idea about the distribution at a very wide scale of air pollutants. A second layer is represented by a land use regression model that downscales this data using urban structural variables, and so assuming that a kind of street or a kind of build can affect the distribution, and so modifying and acting on the data received from the satellite just to describe a more precise distribution of the pollution. In this case, with our system, multi-source system, the third level is generated by the fixed and mobile sensor, provide high-frequency ground truth observation. And so we saw that on the maps I showed before, in which each shell represented in this scale and from data collected starting from the last part of April, represent number reporting the pollution in each point for the different variables measured we are studying. The fourth level is a traffic information system, which explains one of the main emission drivers through fixed sensor, but also through floating car data and app-based queries. All these data are measured values that are compared with simultaneous values that are generated by the model generated by the satellite. In the case we will find discrepancy, this discrepancy became diagnostic information that we can use for validation and local calibration of the land use regression model. The calibrated map and traffic evidence feed the digital twin, enabling scenarios, decision support, and communication with authorities and citizens, and replication also, as we hope, for other urban contexts. But I want to stress, just to close my presentation, that in this approach, we are trying to involve as more as we can also the presence and the participation of the local authorities and also the citizens. Just because there is innovation for us is not only the integration of different data sources, but is especially the creation of a feedback loop between model prediction, ground truth observation collected across the city by mobile sensor, and the active involvement of public authorities and citizens in producing, interpreting, and using environmental logic. This is the reason why I want to close my presentation, thanking you for listening, but also and especially thanking everyone. And I'm showing here some of the people that go from workers of the local authorities to technicians of our institute, to students of the University of Catania that are helping us in applying this multi-source approach and in building the We Wish model. We hope can help us to study and to propose solutions for better wellness in terms of air quality. Thanks for your attention.
Thank you. Thank you very much, Ezio. We come back. Okay, thank you again for your presentation. Are there any questions from someone? Okay, so I just move to the third presentation. Let's see, do we have Alicia, Germania, or Andrade Vera? The title is Secure Microservices Architecture. Is there someone?
Good afternoon.
Okay.
Alicia appears as the presenter in the program, but I will present the work.
Okay. Can you share, please, your screen?
Okay.
Excuse me, who is presenting? Anthony Pacai?
But yes, the authors are Alicia Germania and Andrade Vera.
I think it's just one author, maybe.
No, Anthony Pacai, are you an author of this work? But maybe in the program they committed a mistake because I see only two names.
Yes, two authors.
Giulio.
I think it's just one name. Alicia Germania Andrade Vera is just one name.
Ah, okay. Okay.
Yeah. There might be a mistake.
Okay.
I will notify the administration.
Okay, please. Thank you very much, Giulio.
Thank you.
Okay. Okay, I leave you the floor. Anthony, you can start if you want.
Good afternoon, the members of committee, directors, colleagues. My name is Antonio Pachay. Today I will present my research, Security Microservice Architecture for ICC Topo Cybersecurity Applied to Graph Theory-Based Curricular Analysis System, developed together Alicia Andrade. Today, universities are removing monolithic systems to distribute microservices. At the same time, we use a graph theory to analyze curriculums directed at cyclic graphs. This helps us find academic bottlenecks. However, the curriculum data and student records are data sensitive. Distributing this logic open many APIs and increase the security risk. We found a gap in the literature not existing work to combine security microservice, OWASP, ASBS standard, and student privacy. It is our focus. Our main research question is, how can we design and validate a security microservice architecture for ICC Topo that protects academic data? We prioritize three main security risks. First, unauthorized access to service. Second, data leaks of academic records. Third, the student identification. Our hypothesis is the proposed architecture significantly reduces security and privacy risk without hurting the performance of the curriculum calculation. Our general objective is to develop and validate a security microservices architecture for ICC Topo using OWASP ASBS control. To do this, we defined 4 steps. First, the model security and privacy threats. Second, the select 32 applicable ASBS level 2 controls. Third, design the microservice and trust boundaries. Fourth, validate the prototype with security and performance tests. We defined 2 core variables. The independent variable is our security microservice architecture, which include our security controls and coding practices. The dependent variable is the academic protection level, which we measure using our ASBS checklist. Our thesis is implementing this architecture achieves 84% compliance rate on the ASBS checklist while maintaining a stable latency and optimal performance on their concurrent load. Our design is based on a solid theoretical reference. Works on Handel and colleagues show the internal microservice traffic should not be implicitly trusted. This justified our local token checks. Boundaries support separating authentication from business logic. PAS formalized the curriculum index calculation as a critical asset. When and CAT provided the quantitative model to evaluate ASBS control, and the NIST in 800 provided standard guides or DevSecOps practice. We follow the design science research paradigm. These methods easier for the creating and testing technological artifacts. The research has three phases. Phase one, risk modeling with used stride and security and looting for privacy to prioritize 6 main threats. Phase two, design. We mapped 32 ASBS level 2 controls and established security boundaries. Phase three, validation. We built a prototype and test using real data from University UCSA and UTech University. Let me review the architecture. It's divided in two security zones, north, south, and east, west. In the north-south boundaries, the user interacts with Angular frontend. All requests go through an Spring Gateway or single entry endpoint. The gateway validates external JSON Web Tokens, JWT tokens, limits request rate, and configures secure HTTPS headers to prevent cross-site scripting attacks. In the internal EAS-West boundaries, we isolate service, Spring out, manage credential, password hashing, and multi-factor authentication verification. Spring Core handle academic logic is revalidate the JSON Web Token signatures and enforce the role-based access control. Finally, when the core needs graph computations, it's called to Fast API ICC. Python service restricted to 1 megabyte payload limit. Independent, the PostgreSQL database stores data securely. For validation, so with excellent results, we successful process 52 out of 57 curriculum structure, representing over 2,400 courses. The other 5 structures were correctly blocked due to validation errors. In security, were defined for major controls. First, the token blacklist propagate is under 10 milliseconds during logout. Second, accounts log after 5 file logging attempts. Third, endpoint access is restricted by role. Fourth, multi-factor authentication TOTP is mandatory for administrators. All unit tests passed, and bandit static analysis report 0 vulnerabilities. The prototype is active and deployment with Activity alias. This slide shows the system. Yeah, on left is the main dashboard. This is home screen for academic coordinator and manage students and users. In the center is a curricular analytics new. It shows study plan as interactive graph, red notes, highlights, curricular booklet, and complex course. In the right is the MFA, multi-factor authentication configured page. Administrator must be cast this QR code with their mobile device to enable the TOTP authentication security their account. We measure security using 32 controls from 7 OWASP ASBS categories. The prototype fully implements 23 controls. 8 are partially implemented, such as using environments variable instead of kvault. Only one control is pending, which is anonymity validation on the real student data. Using the WEN and CAT quantitative model, we achieve on 84 weight compliance. This is successful excess or 80% project global, demonstrating that it's a strong security posture. In conclusion, our general objective was successful met. We deployment and validate and secure microservice architecture for ICC Topo. Other specific objectives were achieved. We mapped thread, select ASBS control, design and secure boundaries, and validate performance. The main contribution to this work is present the first operational prototype in academic analysis that combine complex graph calculation with OWASP ASBS security and privacy standards, providing a verified framework for secure university systems. For the next iterations of the system, recommended for actions, first, performing a formal anonymity test with the real data to complete dependent privacy control. Second, integrate hash core vault to security secrets and case, moving the V3 controls to fully implement. Third, automate vulnerability scanning by adding SAST and DAST scanners directly into the continuous implementation, continuous deployment pipelines. And fourth, validate the system with data from another universities to test about this scalability. This concludes my presentation, and thank you for the time attend.
Thank you, Anthony. Thank you very much for your presentation. Are there any questions for Anthony? Okay, Anthony, thank you very much for your presentation, also for keep the time because we were just a little bit longer, so thank you. So we can move to the next presentation. The title is Deep Learning Based Acoustic Event Detection in IoT Edge Devices. Is there someone of the authors? We have 3 authors.
Yes, I think Luis.
Okay, perfect. Luis, can I ask you to share your screen just to give you confirmation that everything is okay?
Oh, sure.
Thank you, Giulio, because when I moved to the program to see the name of the presenter and the title, I can see the screen with the name of people connected with us.
Oh, of course, no problem.
Okay, so I give you the floor, and please, you can start.
All right. Well, good. Okay. Good morning, everyone. My name is Luis Manuel Castro Yagual from Universidad Estatal Península de Santa Elena in Ecuador. This will also include Daniel Quiromba Yagual and Jose Miguel Sanchez Aquino. Today, I will present a paper titled Deep Learning Based Acoustic Event Detection in IoT Edge Device, developed in the context of research of artificial intelligence, applied to a resource-constrained environment. This work motivates via concrete question. It is possible to build an intelligent acoustic detection system that runs on low-cost hardware, preserving user privacy and is accurate enough for real-world application? Or answer is yes, with important nuance about which model to choose and why. The problem is statement. Automatic acoustic event detection has application across multiple domains: physical security, environment, monitoring, smart cities, and in our particular case, educational institutions. However, when we try to bring this capability to edge, that is the low-cost IoT device deployed directly in the field will encounter at least three families of problems. First, adjusting scent variability. In a real environment such as a school courtyard, we can simultaneously have adult conversation, children louder, dog barking, vehicle horns, and emergency sirens. This sound occurs under variable background noise conditions with a different reverberation levels and temporal overlaps. This is a not clean laboratory environment. Second, computational constraint of F device. Microcontrollers such as the ESP32 typically have less than 512 kilobytes of RAM, processing capacity limited to a field 100 MHz, and not high-performance floating point unit. This improves several constraints which deep learning architectures are viable of the device. And third, privacy and bandwidth consumptions. The obvious solution to constantly streaming audio to the cloud for processing creates two serious problems. First, it violates the privacy of the people being recorded, and two, consume bandwidth that is in many environments is simply not readily available. For this reason, our goal was to design a complete pipeline from data capture to the model selection that respects this constraint and enable informed decision before any real-world deployment. And the main contribution, let me explicit about what is this work contribute and what is done not claim to be. First contribution, an custom acquisition platform based on the ESP3266 with an adaptive energy target capture mechanisms. This means the device does not record it continuously. It only records when a relevant event is detected, saving storage, energy, and privacy. Second contribution is a systematic cooperation of 5 deep learning architecture families: CNN, DCNN, GRU, LSTM, and CRNN. Under exactly the same experimental protocol using the same data partition, the same optimizer, and the same evaluation metrics. This guarantees that any observed difference are due to architectures do not methodological advance. And the third contribution is perhaps the most novel from a practical standpoint, is that we evaluate a model not only by classification accuracy, but also by their calibration, how reliable their prediction probabilities are. This distinction is critical for real-time alert system. This is important to note that the study corresponds to TRL23 laboratory validation, and that real-time inference on the ESP3266 remain and future work. Now, the IoT Edge acquisition hardware. For data acquisition, we designed an IoT node based on the ESP3266, the most recent variant of the ESP32 families with a Wi-Fi 6 and Bluetooth 5 support. The nodes integrate 3 case peripheral components: a digital microphone, the ENM-PED 441, which covered the acoustic event of interest, and GPU's module, the Neo Block CM, for event time synchronization, and micro SD module by ESP bus for local storage. The audio is captured in 32 kHz and stored at 16 bits PZ WAV. The most important forward mechanism is the adaptive energy trigger. The device does not recording continuously. Instead, it constantly monitors the RMM's energy level of the audio in short windows, converts an exponential baseline of the ambient noise, and activity recording only when the signal exceeds that baseline by more than 3.5 decibels. This solution is deliberately simpler. It requires no spectrum transformers in real time, operating in streaming mode, and works within the microcontroller memory constraints. In this display, we can observe the node creation. The case is prelim in the 3D, and the data acquisition in education environment in Ecuador. Now, in the dataset, as a result of the acquisition and curation process, we assemble a corpus of 6,400 audio clips distributed across 7 classes: big horse, children voice, dog barking, bat kills, sirens, and ambient sounds, people voice. Those classes were specifically selected their relevance in the educational environment. The distribution is rationally balanced. 5 clubs have 1,000 clips, car horn has 800, and people has 6,000. The dataset has 2 sources: preparatory records captured in the Ecuadorian education settings, and sample for the public urban zone HCAP dataset. This combined one intentional to improve generalization, as we will see later. We apply 3 preprocessing techniques: VAT or voice activity detection, data augmentation, and high frequency radio. The legacy partition deserves a special mention instead of randomly splicing clips on the individual level, which will call contaminate training and test with highly similar samples from the same record event, with a grouping with session keys, source clip ID, session ID, and session. We then apply stratified 17, 15, 15 split over in test group with fixed and seed 42. This guarantees that no recording group appears simultaneously on training and test. Now, in the deep learning architectures, we evaluate 5 architecture families are training under the same protocols: 128 Sphinx multispectrum and 16 kHz, Adam optimizer and learning rate 10 administry, class querying to handle mild imbalance, and early stopping of visualization and off-the-fly augmentation during training. CNN captured local exposure pattern in the spectrograms. TCNN modest temporal evolution through successive utilization with reduced computational footprints. Group with attention captures long-range temporal dependence. LSTN with attention identical architecture to group, replacing the recurrent units with LSTM cells with a long-term memory, giving the greater capacity to retain extended cues in text. And finally, the CRNN with attention. The most complex architecture combines convolutional filters extraction and bidirectional recurrent encoding. Its strength lies in simultaneously capture local spectral patterns and global temporal dependence. Our initial hypothesis was the CRN will outperform the rest precisely because this is combination and complementary inductive bias. In the ablation study, to quantify the impact of each pipeline components, we conducted an ablation study using the CRN after reference architectures. The results are clear. Full pipeline get a macrophone score to 0.95%. Without augmentation, the macro F1 score dropped 3.8 points. We have a high frequency radio modulation get 0 to 90.31% or drop 0.1 points, and we have dual filtering microphone score drop at 6.5 points. Removing bad filtering produced the largest performance degradation in the entire experiment. The intuition is straightforward without bad, silent segmented background noise without event intertwining as level noise, confusing the model with a filters are actually discriminated. This result has important practical implications. Choosing a powerful architecture is not enough. Preprocessing quality is a primary determinant, and an IoT system where resources are scarce, investigating a good correlation pipeline may yield more gain to scaling of the modern architectures. In the domain generalization, one of the most serious risks in the deployment machine learning system is a domain shift. Performance degradation with a model encores acoustic conditions different from those in training. To quantify this, we ran cross-domain experiments between a proprietary recording and the urban zone HK dataset. Mixed training balanced test evaluation and 0.9052% property-only training urban zone HK evaluation dropped almost 14 points. Mixed training urban zone HK evaluation get 0.9025%, and mixed training property only evaluation get a 0.1961%. So nearly 14-point drop with training inclusivity on proprietary data confirms the existence of domain shift. Our data were recorded in a single educational institution in Ecuador with a specific acoustic condition, introducing biases of location, demographic, and equipment that do not generalize automatically. The solution would include diverse data sorted during training. Mixed training covers more than 11 points on urban zone HCAP, confirming that data source diversity is an important generalization factor as architecture choice. We explicitly acknowledged this is a limitation. The external validity of the model in acoustic environments very different from the Ecuadorian settings. different reverberization, different ascent, different climates, and that require additional validation. Now, in the main results, looking at the consolidated results of like I said, test set, CRN leads in discrimination with a macro F1 score with a 0.95% accuracy with a 0.95% and wrote out 0.99%. However, it's easy our expected calibration error is the 0.031.5, that is the second worst. LSTM achieved a very similar result. Microphone score with a 0.95% with a lower AC of a 0.0967%. CNN and GRU achieved competitive F1 score, with GRU showing good calibration at 0.0228%, 25%. And finally, the TCNN achieved the lowest macro F1, but also the lowest AC for all. The 0.018085, this makes it the most honest model in the prediction probabilities. And this is a question. Why does calibration matter? Imagine it an alarm system in a school. If CRNN reports 95 probability of detecting a siren, but that prediction is actually correct on the only 75% of the time, the model is overconfident. This can lead to false alarm or worse, to discriminate critical alert. TCNN with a lower AC produce probabilities that are close to the actual hit rate. Let me take a moment to reflect on what this result means for someone looking to deploy this system in production. For a computational standpoint, CRNN requires the largest parameter count and memory footprint, while TCNN and CNN offer substantially smaller size. For the ESP32C6, which is a limited RAM, this is a non-minor detail. It's made the decisive factor. There is a real tension between three object types we cannot be simultaneously optimized. High macro F1 score typically demands more memory and may worsen calibration. Lower AC often sacrifices peak discrimination and smaller model size compromise root. This is exactly we cannot declare an absolutely best model. The right selection depends on the application scenario. In a security system where a false negative has serious consequence, we prefer CRNN or LSTM. In an environment monitoring system with an automatic alert where false alert carry high operational costs, we prefer TCNN. And in this display, we can observe the trade-off analysis, discrimination versus calibration, where CRN is the best model, but TCNN have the best calibration. The closest work demonstrates that it's possible to build complete repository pipeline for acoustic event detection in IoT environments, for adaptive acquisition to inform model selection. The three keys found are: first, preprocessing, especially bad filtering, is a determinant as the architecture should not be underestimated. Second, no single architecture simultaneously domain the discrimination, calibration, and deficient. Selection must be made explicitly based on the application context using the Pareto frontend and the utility function. And third, domain shift is a real and quantifiable. Training of the single data source produced model with a limited generalization, training data diversity is fundamental. As future work, we plan to explore federated learning to preserve privacy while combining data from multiple institutions, multi-level classification for ascent with a simultaneously event, domain adaptation to provide model portability, and finally on-device inference directly on the ESP32 or similar device like Jackson or Ignano, with the natural step to achieve a higher TRL. Well, this concludes our presentation. We sincerely appreciate your time, attention, and interest in our work. We hope the research has been used and that your contribution will help in the development of future initiatives on this field. If you have any questions, comments, or would like to learn more about our research, feel free to contact us in luisbernalcázar-5499@uce.edu.es. And thank you very much for the attention.
Thank you very much, Luis, for your presentation. Are there any questions from someone? Okay, Luis, thank you so much for your presentation. So we move to the last but not least presentation. Before we saw that was connected with us Q Pam. I don't know if the pronunciation is correct. Q Fam. Okay. I give you the floor. Please, can you share your screen, and I will confirm you that we saw your slides, right?
Okay. Yeah. Let me show you my slide.
Do you need some help, Q?
Sorry?
Do you need help to share your screen?
It's okay. Let me find.
Okay.
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 Can you see my screen?
Yes.
Yes.
Okay, please try to move to the second slide just to be sure.
Yeah. Okay.
Okay, perfect. Okay. Thank you.
Okay. I will start my presentation about my paper. Is about a lightweight side channel resistant to random number generator design for FPGA-based edge AI platform. I am Q, and we come from Ho Chi Minh City University of Technology, and we come with the first motivation of this design, with the background that the IoT devices are increasingly developed in security critical application and to protecting the embedded cryptographic implementation is essential in our current work nowadays. Therefore, we got a security challenge. First, we have the side channel attack exploit from power, electromagnetic, and timing leakage from the device. The correlation power analysis can recover secret key without physics instruction from the attacker. Therefore, our research focus on the evaluate the vulnerability of an unprotected AES implementation to CPA. The second one, we developed an FPGA-based TRNG as a hiding countermeasure against power analysis attack. So, with the problem statement that the main contribution of our paper can be summarized in threefold. We introduce our efficient FPGA-based TRNG hardware core to enhance the security level for edge AI platform. We investigate on side channel analysis attack that may occur on edge device. And finally, we analyze our experiment result based on the National Institute of Standards and Technology and the AES test for the TRNG quality. At first, with the background and related work that we survey, the secure cryptographic system requires a true random number generator to generate the unpredictable keys and nonce for the cryptography algorithm. The FPGA-based TRNG should provide a high entropy and throughput with a low resource utilization for the design, which fit for the edge AI platform, which at limit in the computational resource. These requirements are particularly important in FPGA-based edge AI, where hardware resource and power are limited. Most existing FPGA TRNG optimize only one or two objectives, which they focus on the randomness, security, or hardware efficiency. Therefore, a lightweight FPGA TRNG that simultaneously provide a high entropy, strong side channel analysis resistance, and low hardware overhead for edge AI application remain an open research challenge for this topic. Okay, So next we come with the TRNG design with some key consideration for this. First, we come with the hiding and masking countermeasure against power analysis attack. So we discovered that cryptographic system rely on high quality random number to generate secure key and nonce. So we got the hiding and masking countermeasure to obscure the relation between the computation and power leakage in the chip. The heading, we got two types of the heading. We got the vertical heading, which we evaluate the randomize the power amplitude. Horizontal heading, which we randomize the execution timing to misalign with the leakage traces. And the masking we use to randomize the sensitive intermediate value by splitting them into independent share. The leakage can become independent of the process secret data. Therefore, they can be implemented at both algorithm or the circuit level. But in this design, we only use for the hiding countermeasure, which we focus on the vertical hiding, which we will use to hide the power amplitude of our cryptography algorithms. Move to the next slide. Random number, the second one for the key consideration is that the architecture for countermeasure we separate in the class of the random number. So the random numbers are fundamental to cryptographic system because they are used to generate session keys, non-digital signature, and masking value. If the random number generator is weak, the security of the entire system can be compromised. Therefore, we categorize them into the class of the ING like this. First, with the deterministic ING, pseudo ING, they generate a long pseudo random sequence from a short random seed. Secondly, is the physical true random number generator. And finally, is the non-physical TRNG extract entropy from system activity, such as user interaction, without dedicated hardware. Since this work target on FPGA-based cryptographic hardware, we focus only in the physical ING, which provide us a high quality and unpredictable randomness for secure application. And next, we come with the correlation power analysis on how they got to exploit our key. So unlike a proof of attack, which require a searching of entire 128-bit key space, a correlation power analysis attack recover the AES key one byte at a time. First, the attacker collect the power trace while the device encrypt no plain text, and the hypothetical value, as you can see here. As you can see in here, with the hypothetical values, where we use the Hamming distance model or Hamming wave model to get the power model of your hypothetical values. After that, they will get the hypothetical power consumed from the hypothetical values. And with the measure power trace, they measure from our device, they will do the statistical analysis. And after that, they will got a matrix like this. And they use the Pearson correlation coefficient to calculate the coefficient in here with the highest values in the correct subkey in the correlation power analysis. When the attacker want to attack us by using the correlation power analysis. So with the thing, we come with to simulate this performance to check is correct or not. So in here is the figure illustrate the result obtained from the CBA attack performed on the unprotected implementation of the AES algorithm. As you can see here, the gray line is the number of traces that we chase for the algorithm. The blue one is the correct key, as you can see. They got the higher value, so therefore we will know this is the correct key byte for our device. It can be observed that the correct subkey is clearly distinguishable after approximately 1,000 traces. So we try to put on TRNG a hiding countermeasure, and the result we get is this one. As you can see, they cannot exploit our key anymore, although I put them into like 10,000 traces. They cannot exploit our key anymore when I put the TRNG to hiding my power analysis. So come from this, we come to design the TRNG. So our proposed TRNG adopts a hybrid combination by using a ring oscillator to generate the entropy from oscillator jitter and a ring generator to process and propagate the entropy. The ring oscillator will inject the entropy into the ring generator to improving the unpredictable of the generated random bit. And after that, the ring generator will implement it using a Galois linear feedback shift register in a ring topology with the NAND gate replaced as a conventional inverter for the ring oscillator. The advantage of this proposed architecture, we got the lower critical path delay and from the Fibonacci register, and we can reduce the failure issue come from the Galois LFSR, and it is suitable for a lightweight FPGA-based cryptographic application. So we come with the proposed design here. As you can see, with the black one, we got the RO part, include the number of odd inverter in here, and the NAND gate in here. They take back as the not gate, as long as we put the enable in here, and in here is the linear feedback of the TRNG design. These are the entropy injection bond into this one to generate the output bit stream with the high quality of the unpredictable one. And this is how we have, this is our core, and this is how we implementation the core into the FPGA one. We got the core, we build the main controller, and then we use the UART interface to collect the number of random bits to our PC to implement to our AES, our algorithm, to test with the quality of the RNG1. Next one is how can we test is it the true random or not? We will test with the autocorrelation test and distributed of the raw bit. This is 1 million raw bit we collect from our design. And this is the autocorrelation test from our RNG test. And you can see that all of the bits, they are not correlation together. So therefore, we can ensure that they are unpredictable very high. And the next one is the test from the NIST and the AES one to check the entropy quality. And to pass all of the test, your RNG will become the true random number generator. And after that, we got the state-of-the-art comparison. We compare our work with the other work, use different technique to design on TRNG with the same FPGA family. We use the Active 7 in here, and their result cost is higher than us, which we can put an affordable throughput compared with their design. We balance between the result cost and throughput, and obviously that this can be implemented on the Edge AI platform. And in conclusion, this paper had achieved on TRNG provide a true randomness of physical entropy sources, making them more suitable than PRNG for secure cryptographic application. A hybrid FPGA-based TRNG was proposed as a hiding countermeasure against a side channel attack. The introduced randomness reduced the information leakage and improved the resistance to power and timing by a stack. Finally, an SCA demonstration to an unprotected AES implementation highlight the necessity of hardware countermeasure. In the future, we aim to build the AES algorithm as the hardware base to check the correctness of this design. And this is the reference that I use from my state-of-the-art comparison. And that is all. Thank you for listening to my presentation.
Thank you, Q. don't know if the pronunciation is correct. Are there any questions from the other participants? Okay, no, I think, thank you again. Thank you. So I would like to thank all of you for participating for this section, which see different contribution associated to two different workshops. In fact, we saw that the topics were very expanding several fields of research, but in general, I think that the sharing of the research and the contamination is every time stimulating. So thank you so much again for joined this section, and I think that we can stop for today for the conference and enjoy the rest of the program, even though I think that we are all participants online. So thank you again. Giulio, do we need to do something else?
Thank you, Vincenza. No, there's nothing else needed. The room will close automatically.
Okay, thank you again. Bye all.
My pleasure. Bye. Goodbye.